History is often taught as a straight ascending line. We assume one discovery leads directly to the next. But the archaeological record is intersected by localized peaks, moments where technology reached heights that appear out of sync with their surrounding era. These peaks include the massive subterranean architecture of China's Longyu caves, the carbon-reinforced matrix of Damascus steel, and the long-count celestial tracking of the Maya calendar. These artifacts share a specific signature. They exhibit geometric and physical properties that match the output of modern mechanized manufacturing processes. This creates the archival gap. Despite the engineering density of these projects, we find no technical blueprints or physical schematics detailing their construction. The physical proof exists, but the documentation is missing. This forces an engineering inquiry. How did isolated civilizations achieve this level of precision using a pre-industrial toolkit? And why did these specific technical lineages disappear from the historical record? To find the source of this precision, we look toward the field of archaeoastronomy. Sites like the Maya cities and the Gosek Circle functioned as massive, fixed-point observatories. The Maya hard-coded their observations into stone. By interlocking three separate cycles, the Salkin, the Hob, and the Long Count, they established a tracking system for the orbital movements of planets across thousands of years. Their calculations achieved a margin of error measured in mere minutes per century. They maintained this mathematical rigor without the aid of optical lenses or mechanical chronometers. This diagram shows the Gosek Circle in Germany. Built 7,000 years ago, this circular enclosure served as a macroscopic solar clock, predating the development of formal writing. The structure's physical gates are positioned to align with the sun's trajectory during the winter and summer solstices. This geometric tracking allowed the builders to predict seasonal shifts with localized accuracy. These civilizations utilized earth and stone to build immense mathematical models, turning the landscape itself into a precision instrument for measuring the cosmos. While some cultures focused on the sky, others applied this same precision to the earth through large-scale geotechnical engineering. 5,000 years ago, the Indus Valley civilization engineered complex urban plumbing systems within cities like Harappa and Mohenjo-Daro. Effective sanitation required specific gravitational engineering. This diagram shows the drainage channels, which were built with a continuous downhill gradient to keep water in constant motion. Maintaining optimal kinetic velocity across miles of brickwork required a mastery of fluid dynamics. If the angle deviated by even a fraction of a degree, the system would stagnate and fail. This command over physical laws extended to the excavation of solid bedrock, most notably in China's Longyu caves. These underground chambers were carved with extreme geometric clarity. The parallel marks across the walls suggest a standardized excavation technique that achieved perfectly uniform surfaces across 24 separate caves. We find another example of buried engineering on Easter Island with the Moai. Excavations reveal that the visible heads are attached to fully articulated bodies, extending several meters into the volcanic soil. This indicates a logistical capability for transporting and entrenching massive monoliths vertically. Routing water through a city grid, carving uniform subterranean chambers, and anchoring multi-ton statues all point to an empirical grasp of structural physics that functioned independently of modern industrial tools. Beyond macro-engineering, ancient builders demonstrated a sophisticated understanding of material science at the microscopic level. Japan's Horyuji Temple has remained structurally sound for 1,400 years. Its timber frame has withstood over a millennium of seismic activity and decay. The builders utilized a process for selecting trees based on regional density, followed by a multi-year drying phase. This controlled the moisture content, allowing the wood to resist rot and maintain structural tension for centuries. In metallurgy, Damascus steel was renowned for a combination of hardness and flexibility. These blades could maintain a sharp edge while enduring the stresses of heavy combat without fracturing. Microscopic analysis of these blades reveals the presence of carbon nanotubes within the steel matrix. Producing this required precise control over the iron's carbon content and the thermal environment of the forge during the smelting process. The Roman dodecahedron reflects this fusion of geometry and metallurgy. Cast with 12 pentagonal faces, each containing a hole of different diameter, their mathematical proportions suggest a calibration function. Yet their exact use remains an ongoing debate among engineers. Ancient artisans achieved material properties that we only recently began to replicate, relying on empirical observation and repetitive trial to master their crafts. The physical evidence of these technologies is undeniable, yet the records of their development are non-existent. One theory involves guild secrecy. Engineers and smiths may have protected their livelihoods by keeping their methods within a closed circle, ensuring that no written manual could ever fall into the hands of a competitor. Technical knowledge also relied on oral tradition. When a method is passed from master to apprentice without documentation, a single generation of conflict or disease can permanently erase a complex skill set. It is also possible that these designs were intentionally concealed. Successful empires often treated engineering breakthroughs as state secrets, hiding them to maintain a strategic advantage over rivals. The archival gap serves as a reminder that technical knowledge is vulnerable to loss. Advanced methods are not guaranteed to survive the passage of time simply because they are effective. Modern manufacturing is supported by a massive infrastructure of power grids, CAD software, and global logistics. The ancient toolkit was localized, relying on manual labor and direct physical feedback. This creates a fascinating paradox. We see two entirely different methodologies arriving at the exact same geometric result. Ancient builders bypassed our modern infrastructure by developing an intuitive command of physics and a deep understanding of their local materials. The existence of these artifacts breaks the myth of linear technological progress. They prove that our history contains dead branches, complex sciences that flourished and then vanished. A lack of written blueprints reflects the fragility of documentation, not a deficit in ancient capability. Our history is a record of scientific lineages that thrived, then vanished, leaving only the physical proof of their precision.